now right now, so I'm trying to fix it.
Think about what you can change in terms of the sequence
Okay.
of stitching.
Okay.
One hint I can give you is you don't necessarily have to start from either end.
Okay.
What would happen if you started from the center?
Okay. Yeah, in that case, we will have to go like left and right. Right.
Yeah, that's why some of those stubs have left and right terms in them.
Yeah.
There's other ways to solve it also.
So,
That to get rid of the accumulation of warp errors and all. One way to do it is project it onto a cylinder, but that's a bit more involved, which is why I didn't
okay.
talk about any of that, and I don't expect you guys to do that.
Okay. Like, so you gave those comments in the function, right? Like the steps to follow.
Yeah.
Like if we don't use the like inbuilt CV2 functions, can we do it with other methods also, or should we follow the same steps?
Like what?
Like the way you told, if I try to figure out how we can project it on the cylinder and do, it will essentially not follow the same steps as you mentioned in the comments, right? Like before comments you mentioned.
Yeah, I mean, the general outline of whatever you do, even if you're projecting it to a cylinder, you'll still have to do all the steps leading up to it. I don't care if you change the code a lot. The only things, hang on, I just want to finish setting up. Okay, that's on. I'll be done in a minute.
Yeah.
Okay. Set projecting the norm. Then, okay. Yeah. What did you ask me? Different method. Yeah, I mean the underlying principle and sequence of operations that you'll have to do regardless of uh, what approach you end up taking is you start by computing features, looking for matches, filtering out only the good matches, then estimating what the transform matrix would be, which is your to get the homography that lines up well.
So until the homography matrix, it's already I completed and it's coming. Even the matches I'm able to like show up in the images. Till there it's fine. Now in the warp and stitch function. So there, if I like you have mentioned like few comments like giving the instructions, right? Like what steps we can use.
I don't remember what's in there. Yeah, I mean, a lot of it is because of the way I make these. I first solve it and then take stuff out.
Yeah.
Okay, warp and stitch. Let's see what's in here. Direction of stitch. Images. Okay. Stitching left. Yeah. Yeah. What about it?
So you like in the template you gave us, you gave like
Yeah, I have it open.
yeah, yeah those can scroll down. Yeah, those if stitching left, compute inverse homography, and yeah, those comments you gave, right?
Yeah.
It's like the instructions of.
Yeah, I mean they're hints.
Yeah, so if we do it in, is it necessary that we have to do the same? No, right?
No.
So like overall, we have to consider the direction and not use any inbuilt CV2
Yeah.
like libraries.
Right.
Yeah, so we can if we.
I mean, this is just a sort of, it's a recipe. I'm not giving you an exact algorithm, because regardless of what you do, uh, if you have a base image and you want to stitch, so this is already a composite of something, and you need another transform to map that to a transformed plane, then there is inversion going on to find out what the original would have been over there when you're going that way. Whereas if you're taking an image and moving it somewhere else and warping it, then you're doing the forward transform. So I mean, there's nothing to get what's it? Nothing to fixate on in here. Basically, just as long as you can solve them, it's acceptable.
And I have one more request with the
Yeah.
updated project proposal and report submission. Is it possible to extend that deadline? It's currently scheduled for Friday, right?
Yeah, okay, I can move that to Sunday. Saturday night, actually.
Long weekend, right? I'm planning to go out.
I also need time to grade them, or at least like look at them, right? So if it comes Sunday midnight, then I won't get a chance to look at it till Wednesday.
Like we have like the next project submission is on I think 19th. So we'll have time.
Yeah, I'll check. Mm. How's everyone feeling about the homework? Stuck? Yeah. Yeah, that's why I gave you guys 10 days. Because that's where I also got stuck when I took this class. I was able to stitch 2 images, but then past that, nothing made sense. Either the third image would get really warped, or I'd end up with gaps, and then the 5th image, it's weird. And the solution to that problem has less to do with thinking about it in image processing terms, but just paying attention to what's going on with the images when you stitch them. So a couple of people asked me about this on Piazza, and I didn't post the hints that I gave them publicly. Just I don't know, it feels a bit unfair if I give everyone hints based on what some people are asking me, because they're putting in the effort to tackle the problem. But considering the deadline is, when is it? Tomorrow? Tonight? Okay. Yeah, a hint that I can give, if I can find a marker. There's no markers. Unfortunate. The one time I had something I could draw with relative ease. Anyway, so I was talking about this a little bit. Now, assuming this is the first plane, first image, and the second one that I want to stitch is this, and I was able to find features. Um, the way these images are acquired typically is with a person standing in one spot, and then you like rotate the camera, right? So this is an arc around which the camera is traveling. Which means that you're looking at each plane with a different angle. So if you just put the planes next to each other, then this is probably how it would be. And there's this angle between the reference plane and this one. And when you project uh, this, because we're visualizing everything on one plane, which is our monitor. So um, this we shear so that the parts that are closer to the image look to the camera look larger. So these ends would basically get uh, larger. And then when you're trying to stitch the third image, assuming you already have this one over here, what happens? Because they're trying to map a third plane on here. So there's another angle. And then the third one will have to be warped further. So the more images you stitch, the more sort of warping you introduce. And you're stretching the image, so that makes it a bit blurry. And it's a compounding issue. Whatever warping errors you have are getting accumulated over the span of doing that. So a couple of things that you can do is just the way the matches are being visualized in the code right now, I think it only does the first pair and then all of them at the end. I would recommend just visualizing all matches at every step. Uh, that should give you some sense of what's going on over there. And then think about the sequence in which you're doing the stitching. So if you start at one end and go to the other end, then you're accumulating warping errors as you go through the process. Um, is there a better way to do that potentially, rather than going one end to the other? Anyone have ideas? This is uh, acceptable to discuss because I'm asking you guys. So if hints get passed around, that helps everyone. And the objective is not to get anyone bogged down in this assignment so bad that you end up hating the subject, right? I want you guys all to enjoy the process. Man, how do I? Sorry, my thing is acting up. Okay. 37, that I'm behind schedule. Okay. All right. A hint for the homework would be start from the center and work your way outwards to both sides. So that way you accumulate a lot fewer warping errors. Why is this not playing nice? Jeez.
That one to be ball, so it has to, you said that the calculate the offset.
Yeah, you need the homography transformation matrix. Um, you need both the forward and the inverse operations if you're going both sides. offset because so man, I really wish I had markers. I guess the best thing I can do is maybe. Yeah, but let me try to use this thing. I've never used it before, but we'll see. Document camera. All right. Okay. What did you ask me? Right. So that's the first image. Then there's the second one. You get features, let's say here, and then there's the other set of features that's over here. This is how they match. Now, to account for the scale difference between these points relative to these, let's say these are farther apart, but they're the same feature. That means this particular section of this image is closer to the camera than when it was clicked over here. So to solve that, we do our warp and shear and stuff. And then there's the question of position. So these are coming from the same place, right? This line should be overlapping, so you need to offset that image. Like there's the translation component also. Okay, I think I get what you're asking me. So that's just a quirk of the way I've named things. I wouldn't dwell on it too much. So assuming you already have one image and then there's another one that's stitched on it, something like that, say, and then you want to do your third one. One of the things to think about is what region to look for features in. So if you're operating under the assumption that this would not have overlap with the first image, then odds are you only want to look for it in whatever was added on. That is one aspect. As for what the offset part exactly is, I need to go back to my code and see what that was. Set features. Offset. Okay, so stitch left and right. Yeah, I mean the offsets part, I'd put it this way. Even when you're doing right, that's implicitly part of what you have to do. It's just that I didn't talk about that component, but you still need your transform matrix, and that will implicitly contain translation information. It's just that the way you which image you shift onto which image and how you define your empty matrix and populate the values, you just have to pay attention to it when you're going each side. That's the part that you have to pay attention to and think about. So just be mindful of that when you're writing your function, and odds are you'll end up needing two functions to handle the left and right cases, which will become apparent as you implement it. Okay, running a bit behind schedule. Let's get into it. All right. So last class, we talked about neural networks. The kind of model that we saw was what we call a multi-layer perceptron, where you have weights that go along with each neuron and potential bias when we're using bias terms also. And we also looked at just thinking of it in terms of a feature extraction block followed by a linear model. If we want to apply those to images, then there's a few challenges with using something like that, because we know that they're arbitrarily powerful and have really good representational ability, but they're densely connected. So every neuron in a layer is connected to every neuron in the next layer. That's a lot of connections. And if you're trying to emulate something like extracting hog features in the feature extraction half of the model, typically you calculate hog features by looking in an 8x8 patch within the image by breaking it down into 8x8 patches. And each of those patches yields a set of features, typically 36 elements. So if we apply that to an image, our hidden layer dimensions, once it goes through the hog feature extraction part, would be 32 by 32, because they're breaking down a 256 by 256 image into patches of 8x8. And there's 36 elements in each feature map. So that becomes the total number of parameters that you have over there. And your inputs are also individual values, and there's 3 channels. So that's a lot of elements over there. And all of these are connected to all of these. So simply going from the input to hidden layer, there's 7.2 billion parameters that we would need to keep track of. So to apply gradient descent or any kind of optimization to that to learn a set of weights, there's an impractical amount of computation. So this is the sort of dense connection that I was talking about, where every neuron is connected to every other neuron. And if you can think of the sequence going left to right, and the input image would map to individual, each pixel would map to one neuron over here. And this would be computing something like feature extraction. So the other thing to think about is, can anyone guess why there's these 2 regions highlighted over there? Think in terms of when we were talking about finding corners. What were we looking for? What makes a good feature? A feature is a region of an image that is so the word that I was looking for was descriptive. But the reason these are highlighted is not because they're good regions, but within these regions, if you think about the pixel values, they're all pretty similar. Same goes for over there. Sure, there's some variation locally within that patch, but if you think about it in context of the leaves, then the kind of patterns that you would see over there are they'd be similar to a degree. And those regions, if you just look at those patches, then that doesn't really tell us much about what to expect in the rest of the image. So when you think about dense connections and putting this into a multi-layer perceptron, the way we did with MNIST, where you flatten it and supply every single pixel, then you really only need a few pixels from these regions to describe the whole region because of how little variation there is. So there are a few things that we can infer from just how images typically are, and we can inject that understanding into our how to improve using neural networks with images. So the problems that we've seen, we have way too many weights when everything is connected to everything else. So we would like to have fewer weights. We saw that nearby regions are related to each other, and regions that are far apart tend to be dissimilar. So if instead we were able to look at only certain regions at a time and learn weights for those, then that simplifies our computation a lot because we have far fewer connections, which takes us from n squared to n in this hypothetical case. And those blocks are relatively self-contained. So weights that you would have for this particular block, you'd only need weights for the entire block, since everything that's within it would be to represent similar regions, and everything that's outside of it is different. So you can that sort of handles our the three things that we wanted. Now the way to do that, we've been applying convolutional filters like the Sobel and Pruitt to find edges. What do those do? Those typically have a receptive field associated with the filter when you're applying it to the image. So each time you apply the filter to a region in an image, you're taking a weighted sum of that entire region. So, and that same filter is applied to the entire image. So this does two things. You only have, if you're using a 3x3, a single 3x3 filter, that's 9 values, that's 9 weights that you're applying to the entire image. And depending on what weights you learn, you're able to filter certain things. And the effect of applying the filter is contained to the region that the filter is applied. So using convolutions, we're able to make our network sparse, which is good for computation. And it also injects visual domain specific knowledge that we know, trends that we know about it. It's taking advantage of structure. So, and the main thing to take away from that, all of it, what we're doing is really clever, but we still need to keep in mind that bias and variance have to do with what kind of constraints we put on our model, what kind of assumptions we make. And the more assumptions we bake in to the way we learn a model or represent it, what does that do to the bias? So we said that when we assume that a distribution is linear, we are constraining our solution space to the set of all lines that can be drawn in that sample space. So we're biasing our approach with the constraint that it should only spit out lines. Here, we're biasing it by saying that things that are far apart are dissimilar, things that are close are similar. So we're increasing our bias, which reduces our variance by a little bit, but it's not a big enough change that we need to worry about it, because the trade-off of computational efficiency that it gives us, and also being able to understand what's in the image, is worth the small reduction in complexity, because we don't need that ability for complexity in the feature extraction part when you're thinking of the model in two halves. So there's a few building blocks that are that you'll see commonly, regardless of what kind of image-related neural network you're dealing with, particularly convolutional neural networks. And since it's already in the name, that's the sort of fundamental building block, which is a convolutional layer. Now, convolutions that we've talked about so far have been us taking individual filters with predefined weights and applying them to images. So it's still a similar process where you have an input image. It could be grayscale, it could be RGB, or whatever. So if it's RGB, you have a 3-channel image. And then you process it by applying multiple convolutional filters. So hypothetically, one of them could learn how to find edges, one of them could learn how to find corners. And that's the goal, that we want to automate the process so that the model extracts whatever features are most relevant to the problem that we're trying to solve. And the output, if you have a grayscale image and you apply 64 convolutional filters to it, then you get 64 results. And each convolutional layer, depending on what framework you use, will have a number of filters parameter that goes with the definition of the layer. So however many filters you have there, the input number of channels times number of filters is how many channels your output is going to have. And I don't know if this is immediately obvious, but when I say channels, it's basically I'm stacking them behind each other. So similar to RGB. So if I just apply a single edge filter, I can choose to put values in there already going into it, just to demonstrate stuff. In that case, I'd end up with the filter response corresponding to each input channel, and your output is still a weighted sum, similar to two things, both applying convolutions and also the format of neural network that we saw last class. And effectively, what goes on, filter sizes. Now, if you scale this up to the size of the image itself, assuming it's, say, a 256 by 256 image, then if you use a filter of size 256 by 256, what you end up with is basically a dense neural network, and we don't want that. We want to sparsify our model. So typical values that you see for filter sizes go from 1 to 1 to 11 by 11, 1 by 1 to 11 by 11. And 1 by 1 is kind of a special case because it's used where you don't want spatial computation, but you do things along the channel direction. And the most common one probably is 3 by 3, and then you see the occasional 5 5. So for 1 by 1, you're just taking all of the channels in the previous, in whatever that layer's input is, and combining that without looking at pixel neighborhood in a plane. Filters will usually have the same number of channels as the input image, so it gets so that it's applied to however many channels you have. Same problem as when we were doing convolutions manually. Your image, whatever your filter is, can only be applied by looking at a corresponding region in the image. So you would end up skipping a few rows and columns if you didn't pad it. And the same strategies that we talked about earlier, which is replicating it, wraparound, mirroring it, all of those are still valid and used in convolutional neural networks also. Another parameter for how we use our convolutions is by how far we move the filter at each step. So the way we applied it so far was with each filter, each convolution, we moved it just 1 pixel between applying them, but we can choose to have larger strides. Having a larger stride is effectively downsampling the image because you're only calculating the filter response at farther away pixels. So you don't have a response corresponding to every pixel, and you're downsampling. Now, for neural networks, the simple multi-layer perceptron style model that we saw, it was easier to conceptualize how weights are associated with neurons because the relationship was 1-to-1. Here, what we're doing is we're looking at a region and calculating an output for that, and then eventually going through the backpropagation process, updating our weights. So how do we translate that spatial constraint in a way that we can still represent them as matrix multiplications? So the way that problem was solved, this, I believe, was part of the original cafe implementation, which was one of it's an older neural network framework, which I don't think is really used much anymore, but this was a key insight as part of that, where you take whatever region a convolutional filter would be applied and just convert that to a column vector, stack all of them together. So basically what you have once you stack all of them together is vectors corresponding to the region that each convolution step would be applied to. So this implicitly takes care of kernel size, because if you have a bigger kernel, then this will be a longer column vector, depending on stride. If you're skipping 1 row every time you have a stride of 2, then that doesn't change anything really. You just end up with fewer column vectors. Similarly for padding. So now this is easier to think of as a matrix operation because you have column vectors and applying weights to them, this becomes just a simple matrix multiplication where you would have your row vectors of weights and column vectors of the image, and then multiplying them gives you the filter response. And by stacking all of them together, you're able to compute the whole thing in one go. So here, assuming we have 64 filters, we'd end up with 64 row vectors, and this would be corresponding to kernel size and channels. And this is the original input image space. So these dimensions match. And the output that you get is effectively filter response at each location. The other cool thing that we can do using this is also take care of our weight update step, where calculating the weights, you know the difference between what was expected at your prediction step and what features you have, and you also have your input image. So by representing the delta of a layer also as a matrix with shared dimensions, we can multiply that with the transpose of the im to call representation, and that gives you the desired change in filters. Using that, we're able to calculate our weight update step. Even with all of the sparsity that we're introducing, images are still really large and dense. 256 by 256 is considered a relatively low resolution image, but even that has hundreds of thousands of pixels. This is an example of filter responses once that image goes through a convolution layer. So depending on how many filters are defined. So here there's 3 filter responses that we see. And this looks similar to an edge detector output, but in practice, while that is what the output looks like, at no point during the process of training the model would we explicitly tell it to look for edges. So one of the things that the model will do implicitly under the hood is try to learn filters that are different from each other, in addition to being effective feature extraction filters. So the odds of ending up with 64 edge detector filters is pretty low. And what you'll find is different filter responses, and they're hard to explain what the model ends up looking for, which is still kind of an open problem. We've probably heard of the phrase that deep learning and neural networks are kind of a black box. You throw whatever input into it, and it tends to work a lot of the times, but you don't really know what each neuron is learning or what the filters are. So one of the ways to sort of debug what's going on within a model when it's not doing what you want it to be doing is visualizing the feature maps and see if what it emphasizes as you go through the model. In addition to the convolutions themselves, which are doing the bulk of the semantic information extraction, there's a few other kinds of layers that we use. there's pooling layers, and one of the more popular ones is called the max pool layer, which again accepts an image as an input. So when we say an image, I mean this is an image. So you would typically stack a pooling layer after a convolution layer. And what a max pooling layer would do is within each window that it looks at, it will pick the maximum value. And what that does is it emphasizes strong responses and reduces the size of feature maps that you have to deal with, because the idea is that you're preserving information since you're holding on to the strongest responses while discarding what isn't as strong. And the output dimensions are a function of what stride value you set. There's other kinds of pooling also, where instead of looking at the maximum within a window, you would take the average or the minimum. So that is problem dependent, or it's a design choice based on whatever you're building the model for. The bigger your stride, the fewer output values you end up with. So the more downsampled your output would be. And typically, this is just empirical convention that the pooling region and stride are generally close to each other. 2x2, 3x3 max pooling with a stride of 2 is very commonly used. This is an example of max pooling. So assuming these are the kind of values that you end up with after going through a convolution, so something like this, filter responses, or also called feature maps, applying a 2x2 max pool layer to this with a stride of 2, you would look at whatever the largest value is in this window and plug that in there. And since you have a stride of 2, you look at these. My boxes are a bit off, but that's the 7 from these 4 that it's picked up. And then stride of 2 again. So we looked at these 2. Next, we're going to look at these 2. Yeah, I'll have to fix my boxes a bit, but here the largest value is a 10. And we keep doing that, and that gives you a downsampled version of the feature map that preserves the strongest responses. And so we extracted a bunch of features using our convolutions and pooling. We still need to approximate a function that predicts something using those features. So for that, we use our trusty old multilayer perceptron, which is also called the fully connected layer or a dense layer. When I say a multilayer perceptron, that's a combination, a series of these fully connected layers. So that then we use it the same way that we saw earlier. Just stack that at the end, and that depending on what task we're trying to solve, if it's multi-class classification, we would have however many classes we expect, those many number of neurons in the final layer, and then spit out a probability distribution, pick whichever one is the highest. So that doesn't do anything spatial over there. That's doing the universal approximation part of the problem. So in summary, those were all of the main building blocks that we use. You start with convolution, put a pooling layer after that, and then you'll typically see blocks of these repeated a whole bunch of times so that you get finer features as you progress through the network. And finally, a series of dense layers to sort of bridge the gap between the image domain and numbers that mean something. And since this is only towards the end, it doesn't hurt us too much, even though it's densely connected, because everything up to that point has sparsity. Now, the MNIST example, we've talked about this in a few contexts so far. I think what did we do with this? We did stochastic regression-based classification for this. There's also a KNN way to solve this using K nearest neighbors, but I don't think I covered that. But the same example, we can apply this to our CNN. Oh, we also talked about this in the context of our regular neural network where we were flattening it and putting it through the network. And instead, we can apply it to, we can use a CNN to do the same thing. So one of the, how do I put this? There's a lot of architectures, and this is where the sort of barrier to entry comes into play when in terms of just learning computer vision or deep learning or stuff. There's a lot to catch up on, and quite possibly the first architecture that resembles what we know today to be a convolutional neural network was LeNet, which Jan LeCun came up with in 1998. And this got 99% accuracy on MNIST back then. It has all the same building blocks that we looked at. It has convolutional layers and subsampling, which is similar to the max pool that we talked about. And towards the end, we have a fully connected output. So the broad overall structure and sequence of operations is similar. And this used logistic activations after pooling layers. Nowadays, we have better activation functions, but this was one of this was the first approach that used back propagation to learn weights. The other big milestone in that really drove computer vision forward was ImageNet. And this is a bit deceptive because when you hear the word ImageNet today, you would, if you didn't know what it was, you would think that it's a neural network architecture, but it's not. It's a data set that has a lot of images and they're all labeled. There's a whole bunch of categories, and they also had a challenge that they used to run where a subset of that was used that had 1,000 classes. And the task was to learn to classify for the 1,000 classes using 1.2 million images. And the way these images are organized and the classes are related to each other have a lot of similarity and overlap with WordNet, which is a sort of graph representation of words and how they're related to each other. So the underlying premise is that relationship between labels will sort of translate to whatever image-based visual domain solution people would come up with. And the way this data set, ImageNet, was created was There's AMT's Amazon Mechanical Turk, which is a service that lets you hire people to do data annotation kind of tasks. And back then, that was not what it was intended for, but they came up with that use case where they had a whole bunch of people who would basically be solving CAPTCHAs for a long time. And that's how they ended up with the ImageNet dataset. And that, along with CNNs, are what gave us a first promising approach that could be applied to real world problems. Before that, all of this was just something that primarily mathematicians cared about, and engineers didn't really bother. So the next big step, this is another architecture. Actually, I need to look something up really quick. Don't want that up there. All right, we're still good. Okay, yeah. AlexNet. This was created by Alex Krzyzewski, and this was his group's entry for the ImageNet challenge, and they were able to get a much higher accuracy than all of the previous state of the art, which was using SVMs with SIFT features. Now, when we look at the way this whole approach is formulated and convolutions and sparsity and pooling, downsampling, all of these together, it's a really good combination. They're matrix multiplications, but why did it take so long for that to be practical to use? A lot of us, I think we'd be able to guess what that is. It's there's one piece of hardware that we use a lot today. Yeah. Doing this on like a Pentium processor would have taken forever. So much of the innovation when it came to the AlexNet entry for ImageNet had to do with being able to run CNNs on GPUs, and that was one of the big leaps that we made. He wrote CUDA-ConNet, which must have taken an incredible amount of thinking and effort. And that let them speed up the training process to an extent that made it practical. So this CNNs with GPUs is what really made things take off. So far, the outputs of convolutional layers, I said that they could be similar to edges or whatever. This is visualizations of the filters within AlexNet that was trained for the ImageNet challenge. It's kind of hard to say what they look for, which is why I haven't been saying anything concrete, but that if you remember what the Sobel and Pruitt filters look like, you typically have a bright region followed by zeros, followed by like ones, zeros, and negative ones. So you're going from brighter to darker when you map it to a color map. And you see some of those trends over here. Also, HAR features that we looked at. those had these sort of alternating intensity patterns. So the model learns on its own filters that let it look for features. This would look for edges probably diagonally or high frequency series of edges. The deeper you go, since there's pooling and stuff going on, your outputs are downsampled, which means that when those feature maps go through another convolution and pooling, the outputs are further downsampled. So it gets harder to tell what they're doing. But what we do know is that they are a way to combine the features to um, use the features that are learned at the lower levels as a set of building blocks to look for more complex features as you go through the model. And when you put all of that together, now what you can see is these are outputs of applying each the first filter from each convolution layer to images, and you can see that the things that they look for become more specific the deeper you go, and it discards stuff that doesn't contribute a lot of information to the image. And then when you put all of them together, you see that it emphasizes the things that would be useful to identifying what is in the original input, to guess whether you can tell that there's whatever this animal is. I don't know. Does anyone know? It's that I'll call that a red panda. You really only need to look for the eyes and nose and know that it's kind of furry. You don't care that there's a tree in there or that it's in a zoo, looks like. I mean, if you were trying to do image captioning, then that would be more relevant. And if you fine-tune this model for an image captioning task, you would probably see it emphasize those a bit more. So it also has to do with the objective that the model was trained with. Since this was for the ImageNet challenge, it was trained with the objective of identifying what class is present. So it stands to reason that you would only care about what animal or object is within it. This has to do with understanding what the model is learning. There was information flow mentioned over here. When we have a whole bunch of different kinds of images, since the way these predictions are made is by looking at which of the final neurons has the strongest response, that same process, we can apply that insight to every layer in the model and try to map what kind of image activates what neuron. And when you do that enough, you start to isolate patterns in which neuron gets activated by what kind of image. So there could be one neuron that's sensitive to white flowers. This one's sensitive to brown spiky flowers. This one's sensitive to brown, green, or yellow objects. So anything that has that would activate that neuron, and combinations of those then tell you what class it is. So it's similar to how we were thinking of solving the MNIST problem as breaking it down into smaller problems, looking for curves or straight lines and representing numbers as composites of those features. People have done this, and I'll show you once I'm okay. It's 11:30. I'm gonna stop wherever we end up at around 11:40, and then after that, there's a few interactive visuals that I have that other people made at the end of my slides, and I just realized I haven't uploaded these slides either, so I'll do that after class, and you'll be able to fiddle with those on your own. So back to what we were talking about, understanding what the model does. We can invert the problem and do gradient descent on the image and optimize the image to activate certain neurons or certain layers. So when you think of what this means, you can tell a model to, if you want your model to show us its internal representation of what maximizes the class dog, then you would do this. And this was popular a few years ago. It was called Deep Dream, and you'd see these like hallucinated visualizations of what corresponds to classes in models. Early layers typically respond well to blobs, which is when you have a lot of regions that introduce high contrast when put together. Middle layers, they get finer. So this would probably be correlated with something like, I don't know, wool or fabric or fur. Edges, curves, eyes. And then as you get progressively deeper in the layer, the things that neurons respond to are composites. And this we were able to figure out using the deep dream style of visualization. By trying to find an image that maximizes whatever class you're looking for. So putting everything together, this is still the same thing that we were doing in our linear model, in our neural network multi-layer perceptron model, where you have a series of densely connected layers, outputs equal to however many classes you're looking for or expecting. And then this whole thing is a feature extraction block, which you can further break down into thinking of as low-level, mid-level, high-level features. Another architecture that was introduced after that, this is something that we still use, although it probably shouldn't be used much anymore, but it's really accurate despite being as old as it is. This was from the visual geometry group, which is why it's called VGG. VGG, there were a few variants. VGG 16 is the popular one. And this is typically used as the feature extractor. So depending on whatever problem you're trying to solve, which could be something very different from what it was originally designed for, we know that this is very effective at extracting features. So what we would use something like this for is just get rid of the last fully connected part, freeze the weights of this part, because we know this is good at extracting features, and then stick whatever you want after that to solve your problem. This D variant, I believe, is the one that people refer to when they say VGG16, although the C one would also be a VGG16, since the 16 is for number of layers. But that's the overall architecture. You have an initial 224 3-channel input going into the model, which goes through 2 convolutions that have 64 filters each. It then gets downsampled through a max pool. Then you have a couple more convolutions with 128 filters, pooling again, 256 filters, pooling again, and all the way down here, where once it's pooled, you end up with a single output of 4096 neurons, and then that gets passed into this dense block. And finally, you have your softmax activation to convert that to a probability distribution and be able to get classes from it. So for the kind of metrics that we got, this is error, so this would be inversely correlated with accuracy. It was able to find the correct class within the top 5 probability predictions with an error rate of 8%. So 92% of the time, the correct class was in the top 5 predicted classes. And similarly for top 1, it was about 75% of the time. There's still a lot of computation going on since we have a whole bunch of convolutions. There was a network in network idea where you use 3x3 convolutions to process spatial information and use 1x1 convolutions, 1D convolutions to reduce the number of channels. So here, there's a 32x32 input image, which is going into a 1x1 convolution. And since it's a 1x1, and there's 256 filters in this convolutional layer, you basically, the direction along which you're looking for stuff has changed. You're now computing channel-wise rather than spatially within each channel. And that reduces the number of channels. So it went down from 256 to 128 over here, which means there's fewer 3x3 convolutions that need to be computed. So Google took this idea and ran with it. They built GoogleNet. And this is a sort of teaser of the kind of research that we would see in the years to come, where we moved away from individual layers as being the fundamental block that you think of within a model. And instead of that, we have these modules that are fixed arrangements of convolutions and pooling and whatnot. And these then become the basic building blocks. So you would stack a whole bunch of these together in whatever arrangement. And the motivation for doing that is we're splitting layers. So we combine 1x1, 3x3, 5x5 convolutions at the same level of information along with our pooling, and using combinations of sizes. The 1x1s let us reduce number of channels, and this was able to make computation a lot more efficient. This adds in the 1D convolutions to reduce number of channels. And this is going down to up. So these are inception blocks. And they stacked a whole bunch of them back to back. But we're still including dimensionality reduction stuff in there. So the overall computation information gain relative to how much computation we're doing is an acceptable amount. Is there anything that anyone notices here that's different from what we've been seeing so far? Try to follow this from the input side. What's going on? It's going through here, going through a bunch of inception blocks, and then what's happening over here. We have multiple outputs from one model, but we're looking at outputs at different levels of detail, so to speak, because we know that the deeper you go in the model, the features become more complex. So we're able to use outputs from intermediate layers also and extract those and do something with it. Why do we need multiple outputs? So all of this that we've talked about so far involves learning weights, which relies on error being propagated backward through the model and using that error to guide what weights we learn. Now, when you have something that's this deep, you know what the error is at the output level, and you start propagating that backward. By the time you make a few changes, the closer you get to the start, you don't really have any information remaining because the gradients that you get is just one set of values. How do you use that to sort of extrapolate what direction all of these need to change in? It's hard to keep track. And by the time you get to the initial layers, if you don't have any information on how to change them, well, your initial layers are never going to learn. And those are arguably the most important ones because they're the ones learning low-level features, which are what's used in following levels. So if your initial feature extraction is bad, your model's not going to learn anything. Gradients flow through many layers of weights on their way back. When you use activation functions like the logistic, or when you have small gradients, they may disappear. When you have non-saturating activations or large weights, gradients can explode. So you end up with really big error values that get propagated backwards, and then your weights start getting updated all over the place, and your model just doesn't do anything because again, if the gradients are too small or too large, you can't really decide what direction to change your weights in. So we need some workarounds because doing it this way, it doesn't scale. What works for 2 levels or for a 5-layer model wouldn't work for a 500-layer model. And that's when someone came up with the brilliant idea of what they call residuals. So ResNet was introduced, and they introduced what they called skip connections. So what this does is, in addition to whatever the output of a layer is, it also just passes along the input of that layer. And so what that does is it preserves a lot of information throughout the network in both directions. So this was introduced to address the problem that we talked about last slide of vanishing and exploding gradients, because now you have more of the, you have more context at each layer since you know what went into it in addition to what came out of it. And that, oh, that worked out very nicely. That makes it a lot more robust and easier to train. Okay, so these are a couple that I was able to find just really quickly. One of these I knew earlier. This one I found just a couple of days ago. Oh, the link's bad. Okay. Oh, I have to. Sorry, I just need 1 second. Okay. Let's pull that over here. And so there's a bunch of sample images that they have. What is this? I can't tell. Is that looks like pizza? Oh yeah, it is pizza. There's convolutions applied to each channel. However many filters get applied to it. Looks like there's 10 filters being applied. So there's filter responses for each of those. And that progresses through the model. And for each channel, there's different things that it emphasizes. So the example that we saw earlier where, what was it, yellow or green round objects activate certain neurons, this would sort of correlate to something like that. I'm not able to interact with it the way I would like to. But yeah, I'll go on to the other one, which has, this is a guy named Chris Ola who came up with a bunch of very cool visualizations. And there was one in particular, I think it was called an atlas. Yeah. All of these are worth looking at. It's just not immediately obvious what the difference between some of them would be. So using the deep dream kind of approach, they were able to sort of plot a space of labels and how they're organized relative to each other. So coral, fungus, cauliflower, these would be visually somewhat similar to each other and a lot more. If you go over here, you have things that have less texture and are smoother. So what axes these samples are organized along is hard to say, but by looking at them, we're sort of able to reason about where a certain class might be. And this is also how it's at least how I think about what goes on under the hood in like a language model where you have a a series of tokens, and all of those get converted to embeddings. And what an embedding represents is basically where in this hyperplane a sample would be. The reason this is sort of clustered together in some spots, sparser in other spots, is because this is a 2D visualization of something that is not two-dimensional. So in an ideal representation, higher dimensional, these would all be on orthogonal axes and spaced out a lot more uniformly. And the axes could be things like how furry something is, or how white something is, or how hard or spiky something is. So along those parameters, we're able to map classes. In addition to that, like there's all of these are worth looking at. So I would encourage doing that after class. Visualization, no, it's not that one. What else was there? I think teachable machine. This lets you train a network directly in your browser. And I think, I don't remember if this also had visualizations. Anyway, yeah, I'll add a link to that, and feel free to play with all of those. Yeah, that's about everything for now. Okay. Yeah. So I'll share these, play with them. If you have questions, Piazza or office hours. Oh, right. Yes, I remember now. There's also this quick demo that I had whipped up earlier. So I think this should help cement the idea of what we do with neural networks. So I keep saying that we're trying to approximate functions, right? Simplest example would be to take the sine function, and to train a model, you need a set of inputs and a set of targets. So how we get those is by sampling the sine function. So when you think of it in continuous terms, this is what your graph would look like. And then we sample it at whatever resolution we want. So think back to the Nyquist rate. When I reduce it all the way down to one sample, it's there. So you can't really tell much about what the function might be. So we add a few more samples. And that sort of approximates what the shape of the curve is. I'll reduce it a bit more just so we don't make it too easy. Yeah, something like that. And now this whole thing is in NumPy, but typically that is not how it would be done. We just have one single hidden layer with 10 neurons in it. Our input is whatever the value of the sine function is. So the goal is that given a value, we would be able to predict what its sine would be. There's one weight, one bias for the hidden layer, one weight matrix and one bias matrix, and there's also one weight matrix for the final output layer, which is just one single value. in our case. There's the forward propagation where we're getting predictions with a tan H activation function in between there. This is the back propagation part. And the way we train it is by plugging in X, which is our input, Y, which is our value, and making a prediction using the input and comparing it with what it should be from the actual sine function. And the loss is just the average of squared errors. So mean squared error loss is what we're using here. We do this for 1,000 samples, just regularly spaced samples in the range of 0 to 360. And so this is in radians. I called that 360, and then we get 1,000 values, plug that into the sine function, which gives us our ground truth labels. Since we already know what function we're trying to approximate, in the real world, we don't have that information. And then we make our forward predictions, propagate the error backwards, and that will give us some sort of an approximation. So I'll do this for a bit fewer epochs. So when I here, what I changed just now was the learning rate, which is how big the updates are. So what happened here is the gradient exploded just because it's a really trash network and we're trying to do it too fast. So I slow it down a little bit, and now it's able to reduce our loss over the span of 10 epochs. And one epoch is when the model is exposed to however many input and target pairs you have that make up your entire data set. So the data set that we built contained 1,000 samples. So one epoch is training the model on 1,000 samples. And we do all of that and plot what it has approximated. Now, this isn't very good, but it's still somewhat similar to what the actual function was. We can improve that by training it for longer, by increasing the number of samples we have, by making our model more complex or simple, by tweaking the learning rate. So here what I did is I chose to train it longer in the hope that our average loss reduces even further, assuming that 1,000 samples is good enough for the problem that we're trying to solve. And once that's done, in theory, this should be a closer approximation. Okay, so that part's done. And the curve that we get, which is the orange dotted line, is a lot closer to what the actual sine function would look like. And given new samples, we want to be able to predict where they would be. So these are samples where we're supplying the angle value, and it's predicting what the output of where each of those points would lie on our approximated function, and it's very close to what the true sine function would be. So this summarizes the whole process pretty neatly in a compact package. So I'll share this also, and you feel free to play with it. future homework will be something CNN based. I haven't decided yet, but the objective of that would be to like build the actual model and visualize intermediate representations and stuff, and that will be in a respectable framework, not that NumPy is not respectable, but for the particular use case, we'll be using PyTorch, which is what most research is done in. And compared to using something like Keras, which is easier to work with when you're starting out, doing it in PyTorch, you have to deal with the weights and stuff. So that will cement the understanding of what's going on in terms of weights and biases and why we use those and how we make our predictions, because you have to write the forward and backward steps yourself. Also, dealing with the gradients, keeping track of them. Those are things that you have to be mindful of, which encourages thinking about it in linear algebra terms, as opposed to thinking about it in software terms like you would if you did Keras. But once you're out of here and on the job, then whatever the task demands is what you will be using. Yeah, that's it. I went over time a little bit. My apologies. That's everything that I have for today. I can take questions if anyone has them regarding the project, regarding homework, whatever. Yeah.
For the homework, the final image, you need it to be grayscale or just like the color?
No,
That should be
color.
fine. Yeah, because I see like the first part, you're just looking for the grayscale, and also over here, this is original, like the original code you shared.
Grayscaling,
for the matching.
you would do that, yeah, for feature extraction.
Yeah,
And beyond that, like how you visualize it, it doesn't matter.
okay. Yeah, and also here, I just disable this part. I just don't know if you want to show the like the step by step how we get the final image over here from like the.
If you can, that would be good.
Um,
And
scroll back.
preferably, do you mind if I like scroll through a little bit? Could you set it down there? Please.
Yeah, it's just.
You're looking for contours, Stitcher.
Yeah.
You can't be using that, because that solves the whole problem for you.
You said I cannot use it?
No.
I thought that was some. And now I go back and.
Because then the Stitcher handles all the feature extraction and
Stuff. Like.
yeah.
I got this
Mhm.
image.
Yeah,
but
that's pretty good.
I wanted to crop this black part, but
You don't need to, because I mean, if you think about the outline of your image, it's not a regular rectangle, right? You
Yes.
have stuff that's going up and
okay, so this would be fine.
yeah, yeah.
For the progress report of the proposal, you have to push the code and repo submit screenshot. Like, what's the requirement?
First propose. Yeah, you're talking about the first like update.
Yeah, the submission behind proposal.
Proposal should be in the same format that your original proposal was in, and Yeah, your first update, just whatever you can visualize, if there's anything.
Screenshot making report, like
yeah,
how we
yeah,
make
yeah.
reports.
Your code, I mean, I don't expect to read through your code, but I'll still look at your repos probably just to see if there's any commits or whatever.
Like,
I mean, if
currently
you're
we're working on like a local device, we haven't pushed anything, so we need to push it, right?
what have you done so far?
Like we have processed, we have used implemented Yoga and processed like a small 50-second.
50-second
video.
So you would have written some code to do that,
But
right?
it is local, so we'll push it after say they have to submit it finally.
Yeah, I mean,
And then submit
local and version control, they're independent. They don't have anything to do with each other. So like, regardless of where you're developing something, the objective of using it is just to keep track of like checkpoints, right? Okay, I finished writing my pre-processing, I finished writing my data loading, whatever. So that's all.
Screenshot or just that.
Uh,
What do you expect in the progress report?
that varies a lot from project to project, right? Whatever you think is most significant towards the completion of
So
your
there's no
project.
structure like what you feel like putting, like you can do that, right?
Yeah. So if you have been working on the like data side of stuff rather than the method, then that is what you would include screenshots of whatever pre-processing you did. If you're generating an augmented data set, then talk about what augmentations are doing. Put a couple of examples if you're doing things like color jitter or whatever, which is not immediately obvious. Because flipping, it's already covered, so there's nothing new. Whatever you think is new and you find engaging, basically, that's it.
You're using Swing unit for our project. So can we refer code somewhere?
Yeah. What is your elevator pitch for what your project is? Just to remind me.
Crowd computing.
And okay. So is like Swin unit the core thing?
Yeah,
Or
that's the model that we're creating again.
so okay, let me put it this way. If you use their implementation directly, what does that leave for you to do?
Refer Swing customer.
Yeah, I'm not saying that that is what you're doing, but hypothetically, if you pick the canonical implementation, use that directly.
Someone did implement the unit by ourselves. Maybe
That's for later. I'm saying if you took it and just trained it on your data, say, what else is there that you would be doing?
count the number of people that from
Okay, so logic required to convert your output segmentation map to a count of people, right? So that is when you're doing, what is it, instance segmentation or semantic? I forget the difference. One of those cares about multiple instances of the same class. So yeah, so if you if you formulate it as an instance segmentation problem, then you get your number of people directly by design.
the bank.
Uh, what I would suggest, if you want, I mean, it's already been what, a week and a half, right? And these aren't even like simple to wrap your head around if you want to build them from scratch. So I am not going to ask you to do that. Okay, how about this? You can use swing transform